Thank you. Welcome back once again. We're still on physical interpretations, and this physical interpretation 2, we want to look at more interpretations from the outcome of the Schrodinger equation. We're going to look at the structure of many electron atoms, penetration and shielding, spin orbit coupling, illustrations, and conclusion. The structure of many electron atoms. Remember, we'll be looking at hydrogen atom. We want to quickly look at when there are so many other electrons, that is, many electron atoms. In terms of many electron atoms, the actual wave functions of these electrons are complicated, because we have so many electrons. However, the orbital approximation simplifies this to some extent. This says that a reasonable first approximation to this exact wave function is obtained by thinking of each electron as occupying its own orbital. Hence, writing phi r1 r2 will be equal to phi r1, that is a wave function for each of these electrons separately. We can think of the individual orbitals as resembling the hydrogenic orbitals but with nuclear charges. So that means these nuclear charges are modified by the presence of all the other electrons in the atom. This is the approach, but it helps us to, it's an approximation actually, but it helps us to discuss chemical properties of atoms and actually helps to make more, findings of atomic orbitals. Take the hydrogen atom as an example. We'll report the configuration of hydrogen as 1s2. That is, the single electron is in the 1s orbital. For helium, the second electron joins the first in the 1s orbital, and so the electron configuration of the ground state is 1s2. The next one is lithium, atomic number 3. The third electron cannot enter the 1s orbital because the orbital is already filled. It now enters the next available orbital, that is the 2s. This also fills when it accommodates 2 electrons. When this happens, the next is 2p, and so on. So we have 1s, 2s, 2p, 3s, 3p, 3d, and so on. Electronic configuration of all these elements in multi-electron systems. When we have many electrons, then the case of penetration and shielding comes in. In many electron atoms, unlike a hydrogenic atom, the 2s and 2p orbitals, and in general, all subshells of given shell are not degenerate. 2s and 2p are not, even though they have the same principal quantum number of 2, the angular momentum quantum number are not the same. This s angular momentum here is 0, while angular momentum here is 1. That's for 2p. S electrons generally lie lower in energy than p electron of given shell, and p electrons lie lower than d electrons of given shell, and so on. Now, this is why an electron in many electron system experiences a Coulombic repulsion from other electrons present. So there are so many other electrons, the first electron, second, third, fourth, and so on. So there's Coulombic repulsions between the electrons. Now, because of that, it experiences repulsion. The nucleus is taken as a point. Electron is represented by a point negative charge, and the nucleus is a point positive charge. And of course, at a distance of radius r. The negative charge reduces the effective nuclear charge of the nucleus from Z to ZeFF. So what the electron, let's say for instance 2p, will be experiencing will be an effect that is reduced by the presence of 2s, which is in front of it. Of course, that is what we call, where ZeFF is called effective atomic number or effective nuclear charge. Therefore, the electron experiences a shielding nuclear charge, and that the true atomic number is reduced to ZeFF. by an amount called the shielding constant. So the actual atomic number that electron will get will be ZF minus Z. That is the original Z minus the shielding constant of that electron that is more penetrating. Electrons do not actually block the full Coulombic attraction of the nucleus. The effective charge is simply a way of expressing the net outcome of the nuclear attraction and electronic repulsion in terms of a single equivalent charge at the center of the atom. We're trying to explain now. An s electron has a greater penetration through inner shells than a p electron, in the same sense that it is more likely to be found close to the nucleus than p electron of the same shell. Since only electron inside a sphere defined by the location of electron contribute to shielding, the s electron experiences less shielding than a p electron. So s electron is more penetrating and experiences less shielding. Consequently, by the combined effect of penetration and shielding, s electron is more tightly bound than a p electron of the same shell. Similarly, a d electron penetrates less than p electron of the same shell, and therefore experiences more shielding and even smaller effective nuclear charge. Spin orbit coupling. Now we have electron, it has a spin and it also has a orbit. Remember, there's an orbit and there's a spin. So the difference between the singlet and triplet states, of course, I think we'll still meet this singlet and triplet again when they are paired and when they are like this, that is unpaired, is the Coulombic interaction which results to quantum mechanical effects. So electronic configuration, sometimes you see this, sometimes you also see that. Another effect stems from magnetic interactions of the electron. So we see these electrons also have magnetic, of course we know we have magnetic quantum number. So there is a spin quantum number, there's also a magnetic quantum number. These interactions is weak for light atoms, but for heavy atoms may be comparable to the Coulombic interaction and have marked effect in the energy levels of the atom. Because of the electron has spin angular momentum and because moving charges generate magnetic field, this arises from its spin. Similarly, an electron with orbital angular momentum is in effect a circulating current and possesses a magnetic moment that arises from its orbital momentum. So the interaction of this spin and the orbit is what we call spin-orbit coupling. The strength of the coupling and its effect on the energy levels of atom depends on the relative orientations of the spin and magnetic moment, and therefore on the relative orientations of the two angular momenta. It is common to describe spin-orbit coupling in terms of coupling of an angular moment to give a total which is specified by a quantum number J. In an atom with orbital quantum momentum of L, angular momentum quantum number L, the spin can be aligned parallel or anti-parallel. We have seen that it can be parallel, it can also be anti-parallel, where one is facing up and one is facing down. And the resulting value of the total angular momentum quantum number is J equal to L plus half or L minus half. Now it means that, for example, an electron in the p orbital L is equal to 1, so which will give us either 3 over 2 or half. 1 plus half will give 3 over 2, and 1 minus half will give us half. Therefore, this difference arises, that is the different value of this J arises from this angular momentum quantum number, this L plus half and L minus half, and we call that the different levels of the configuration. Illustration: calculate angular momentum that arises from d electron with spin and s electron with spin. So in each case, we're looking for the possible values of J. For a d electron, L is equal to 2. So there are two levels, which is either 5.2 or 3 over 2. Remember, 2 plus 1 and 2 minus 1. For S, we have 0, so it's only 1, that is a half. We have to note the dependence of the spin-orbit interaction on the values of J is expressed in terms of the spin-orbit coupling constant, A. A quantum mechanical calculation leads to the result that the energies of the levels with quantum numbers S, L, and J are given by this equation. Equation 3 is very important. Hence, the different levels, we use this to calculate that coupling, as seen in the next example. We use that to calculate. Just pause this video and check the calculation. The first part of that equation 3, we'll put the values of our L, and then we'll calculate and substitute and we'll get that value. Thank you so much for your time. We've looked at structure of many electron atoms, penetration and shielding, spin-orbit coupling, and looked at some illustrations. Thank you very much, and I expect to see you in the next module of the class.